Hello trigonometry students, my name is Jami Emigh and this video starts our discussion on chapter 4. Title is Graphs of the Circular Functions. Many things repeat with a predictable pattern naturally. Right here, this is a periodic graph and it represents a normal heartbeat. You can see how it's repeating. Each time that it repeats itself, we call that a period. Let's talk about in general. A periodic function is a function f such that f of x is equivalent to f when you input x plus np. What are x, n, and p? Well, x is real numbers that are in the domain, n is any integer, and the positive real number p represents the period. A couple more examples here. We can see that the tide, we have low tide, high tide, low tide, and then it repeats, high tide, low tide. Here we've got the sun. If you track the way it's setting, rising, and then setting, looks like the sine function. Let's talk about the sine function in general. Here we have one period of sine that we just looked at, similar to the sun rising and setting. So in this graph, we actually are looking at now two periods of the sine function. It does extend forever in both directions, but this right here is a snapshot of two periods of the sine function. F of x equals sine of x. X has to be between negative 2 pi and positive 2 pi, including negative 2 pi and positive 2 pi. The domain of sine is negative infinity to positive infinity, or all real numbers. The range on sine is a negative 1 to positive 1. I like to think about the height of sine. You can see here that this curve is bouncing between positive 1 and negative 1. That's the range. Each period is 2 pi. I like to think about the unit circle. One time around the unit circle is 2 pi radians. Same thing here. Sine, I'm starting at the origin. If we go here, we're at 90 degrees, or a quarter of the way around, or pi over 2 radians. And then the other quadrant here, this would represent quadrant 3 on the unit circle, and this would represent quadrant 4 on the unit circle. So just like traveling one time around the unit circle, here we have 2 pi radians will complete one period of the sine function. The graph above, like we said before, but now it's in writing, we have two periods of the sine function in this particular graph. Although we know by the domain, negative infinity to positive infinity, this would repeat forever in both directions. X-intercepts, we're often interested in those. Those are sometimes called the roots or the solutions, should it be set equal to 0. The x-intercepts for the sine function take on the form any integer times pi. The ones we have in this little snapshot would be negative 2 pi, negative 1 pi. Here again, it intercepts the x-axis at 0 pi. Here again at 1 pi, and here again at 2 pi. And that would continue, making all the x-intercepts in general have the form of any integer times pi. Sine is an odd function. That means that it's symmetric with respect to the origin. For all x in the domain, if you take sine and you input a negative x into it, the output will be the negative of sine x. That's one identity that we're going to want to write down. We're going to be using that to work through any algebraic manipulations we have of equations in which identities are going to help us. Over here we have a table of some frequently used, or another way to title them would be the special radian measures and the quadrantal radian measures. So we looked at these on the unit circle. We were calling them special angle measures or quadrantal angles. We're just in radians now. So before it was 30, 45, and 60 degrees. Here we're talking pi over 6, pi over 4, and pi over 3 radians. The y-coordinate is the same, whether we were talking about theta and angles, or if we're talking about radians here. The y values are 1/2 at pi over 6 radians, radical 2 over 2 at pi over 4 radians, radical 3 over 2 at pi over 3 radians. All right, let's move to our first quadrantal angle. That would have been 90 degrees if we're talking theta, but in radians, that'd be pi over 2. And at pi over 2, sine has a value of 1. Next quadrantal angle would be theta equals 180 degrees, or here, radians, pi many radians. At pi many radians, sine has a value of 0. Next quadrantal angle, theta equals 270 degrees. Here, that's the same thing as 3 pi over 2 radians. At 3 pi over 2 radians, sine has a value of -1. And then 0 and 2 pi, we know those are the same quadrantal angle. In radians, it's 2 pi. In degrees, you would see it as 0 degrees or 360 degrees. And sine at that many radians has a value of 0. So this table right here frequently used the special angles and the quadrantal angles, but in the radian form. All right, so that's sine in general. Let's talk about cosine now. It looks very similar to sine. At quick glance, you might not even think that it changed, but the major thing, or the main thing a lot of students pick up on that this is cosine rather than sine is it doesn't pass through the origin. So let me just go back one slide. See here, sine passes through the origin, increases, decreases, increases again. Cosine, on the other hand, does not pass through the origin. It starts up at its maximum y value of 1, decreases to its minimum y value of -1, and then increases. This right here is one period of sine. Cosine, I mean, sorry. So again, we have a snapshot of 2 periods of cosine, although we know that these periodic functions continue in both directions. So the domain for cosine is the same as it is for sine. That's -infinity to +infinity if you're in interval notation, or you can say all real numbers for set notation. The range for cosine is also the same as the range for sine. You can think of it or see that it's bouncing between +1 and -1. The period for cosine is also 2 pi. So all three of these are the same for sine and cosine. Domain, range, and period. All of them are the same. The graph above, just like in our last visual, is 2 periods of cosine. And now here's our first change or difference between sine and cosine. The x-intercepts for sine were of the form just the n pi right here. But cosine does not intercept the x-axis at n pi. Let's check out where it does intercept the x-axis, just using our examples here. It intercepts the x-axis at -3 over 2 pi, here again at -1/2 pi, here again at +1/2 pi, here again at +3/2 pi. So those, continuing in both directions, take the form pi over 2 plus any integer times pi. Another difference between sine and cosine is that cosine is an even function. That means that the graph is symmetric with respect to the y-axis. For all x in the domain, if you take cosine and you input a negative x, that will output the exact same cosine x. So that's another identity. This one is easier to see using the graph, so I'm going to try to highlight this for you, okay? Try to follow along here. It says that even functions are symmetric with respect to the y-axis. So if I were to take this picture right here, and if I had it in my hands, and I was able to fold the paper along a very specific line, that line, or the mirror, if you want to call it that, would be the y-axis. See how it says the graph is symmetric with respect to the y-axis. So if we were to fold this along the y-axis, one straight fold, then this side, or this period of cosine, would fold and map directly onto this one here. Every point over here would match almost, if you want to say match, that's fine, to every point on the other side of the mirror. So we call that even when it is symmetric with respect to the y-axis. Now let me talk about the identity a little bit. It says that if I take cosine and input a negative x value, I'll get the same had I inputted a positive x value, the same positive x value. Let's check. All right, if I take cosine, I'm going to input negative pi over 2. All right, so cosine of negative pi over 2. Well, the value of cosine at negative pi over 2 is 0. This might not have been the best example to visualize it, but let's keep going with it. Now let's take cosine and input the corresponding positive pi over 2. Cosine's value at pi over 2 is again 0. So for cosine, it doesn't matter if you're inputting a negative x or a positive x, you're getting, or the same positive x, you are getting a value that's equivalent because it's symmetric about the y-axis. Let me do another one that might show the height better. Here we go. Let's input cosine of negative pi. If we input cosine of negative pi, cosine has a value of, we're down here at the minimum, negative 1. Now let's input the corresponding positive x, that would be over here. If we input positive pi, so cosine of pi, we have a value for cosine of, once again, it's down at its minimum, negative 1. And that makes sense if you think about the symmetry across the y-axis, them matching up. So that is what makes cosine an even function. If you didn't really understand that concept of even and odd with sine, that's understandable. Cosine is a lot easier visual, and it lends to the understanding of the identity, whereas now that you've hopefully understood why cosine is even, go back and it might make more sense to you why sine is odd. I'll just show you quickly. If we were to fold sine along that same y-axis, this side of it, right here, this period, would not match up with this side right here. It wouldn't match up with this period. That's why it's odd. Furthermore, the identity, if we were to input sine of, let me go with one that's going to give us a visual. Right here. Let's input sine of negative pi over 2. At negative pi over 2, sine has a value of negative 1. Okay? Now let's input its corresponding positive pi over 2. So that's here. Sine of pi over 2 has a value of, not the minimum, here at pi over 2, it's its maximum of positive 1. Hopefully that will help you to see why the identity sine inputting a negative x will give us negative sine of the corresponding positive x. Oops, here we go. Just like that table for sine, I wanted to give us a snapshot right here of cosines, special angles, and quadrantal angles in radian form. These ones come up often, so you're going to want to know them. Okay, so let's talk about transformations of these. We're going to start calling them parent functions. The last two pictures that we saw, we're going to call those the parent functions. Sine of x, that's going to be the parent function. Y equals cosine x, y equals tangent x. This is how we see it here. As these parent functions, though, there's a lot of invisible or implied values. Let me show you. We see y equals sine x. However, we do not see all of this implied stuff. Y is equivalent to 0 plus 1 times sine of 1 times the quantity of x minus 0. All of this right here, if we simplified it, it would just be equal to sine x. None of these things change the value of sine x, as 0 addition of 0, subtraction of 0, multiplication of 1. That's because 0 is the additive identity and 1 is the multiplicative identity. So they don't change our value of sine. However, we want to start highlighting these zeros and ones because when the parent function, that's this one, okay? That's the graph we just saw. Sine x, it's the one that started at the origin. One period looked like that, okay? When we transform that parent function, it's going to be dependent on these implied zeros and ones that we never really paid attention to before because they were implied. Let me break that down further. This right here, we're going to call lowercase a. That's going to be the coefficient in front of the trigonometric function. This right here, the coefficient factored out in front of the x, is going to be our b. This up here, we don't write 0 plus what we're working with, but we're going to identify if there is anything plus what we're working with. We're going to call that lowercase c. And the last 0, anything being subtracted from our variable, we're going to call that d. Okay, so we're going to use the alphabet. We're going to go in order A, B, C, and D, lowercase, and it's going to paint us a picture of how the ways that the parent function can be transformed. All right, here we go. C plus A times sine of B times the quantity of x minus d. You are going to want to keep this written on a flashcard or somewhere for quick reference as you're learning these transformations. We are going to be referring to A, B, C, and D, and you want to know which ones they are. So have this for you somewhere that you can quickly reference. Now the sine part, that's the trig function. That could change, okay? We're going to start by talking about sine and cosine, but this general form holds true for all of our trig functions. So it could be cosine right here, could be tangent, cotangent, secant, or cosecant. But we're going to start with sine and cosine. They're the most straightforward. Okay, if our lowercase a is not equal to 1, that is going to change the amplitude. That means that our parent function is going to have a vertical stretch or shrink. If you've ever listen to music on certain machines that show the amplitude, it shows the height of the, it's oftentimes like dots that go up or go down. And when the amplitude increases, they go higher and corresponding lower. When the amplitude is turned down, or when the amp is turned down, those dots don't jump up as high for each period. That's the amplitude. The parent function has an amplitude of 1, okay? We never saw it or talked about it because it's implied. If the coefficient is 1, we don't write it. But if the coefficient is not 1, then our trig function is not going to bounce between positive and negative 1. It's going to change the amplitude according to whatever a is equal to. So when we see an a not equal to 1, we're going to think, all right, change the amplitude. It's kind of nice. Amplitude starts with a. If a is negative, then our graph is going to be reflected in the x-axis. You can think back to our visual here when we were talking about reflection in the y-axis. This is different. Reflection in the x-axis means take this graph, if you had it in your hands, and you fold it along the x-axis. This is like the mirror. So if a is negative, this graph will be reflected in the x-axis. Let me just sketch that. So this reflected in the x-axis would look like, watch this, it goes like that, and that, and that, whoop, and that, and that, okay? So that's what we're talking about if a is negative, which was right here. The graph is reflected in the x-axis. If b, which currently up here, b is this constant, it's currently a 1. If it does not equal 1, however, the period is going to change. that means that the parent function is going to have a horizontal stretch or shrink. So it's not being amped up or amped down. A does that. B, on the other hand, affects the period of the parent function. It can make it take longer to complete one cycle or shorter, depending on B. So let's see. Remember that B affects the period, okay? A affects the amplitude, B affects the period. All right, C. Our current C is this implied 0. But if C does not equal 0, then our graph is going to slide up if C is positive and down if C is negative. Now, notice it's the word slide, not stretch. So to slide a graph up, it's almost like picking it up with your mouse, moving it up and dropping it somewhere higher, or down if C is negative. Pick the graph up with your mouse, drag it down, and then drop it somewhere. You didn't stretch it or shrink it vertically or horizontally. You slid it, okay? So C is going to affect if the graph is slid up or down. If C is 0, it's not slid up or down. It's just like the parent function. Last one. If D, okay, D is currently what's being subtracted from X, which in the parent function, nothing is being subtracted from X. That's why we have minus 0 shown. But if D were not equal to 0, then that graph would slide left if the, introduction of a new word, argument, that's right here, okay? Right there. That's the argument. Here it is again. This is the argument, okay? This is the argument. This is the argument. We call it the argument. If the argument looks like this, x plus some value for D, then the graph is going to slide to the left. It will slide to the right if the argument looks like this, x minus D, okay? So x plus D, our graph is going to slide left. And again, I'm using the word slide. So that's like picking it up with your mouse, moving it to the left and dropping it. You haven't stretched or shrink it. You're just moving it, sliding it. And if the argument looks like this, x minus D, we're going to the right. Notice that the negative comes from the derived formula. So we'll see in some examples how this negative D can be a little misleading. But when you're talking about just transforming the graph, if you see x minus a value, slide it right. If you see x plus a value, slide it left. And for me, it helps to think the plus sign looks like a bunch of L's. So if I see x plus a value, I slide that left. All right, let's talk about the amplitude in a little more detail. The amplitude of a periodic function is half of the difference between the maximum and the minimum values. The graph of y equals a sine x or y equals a cosine x with a not equal to 0. The amplitude is a distance, so it's going to be the absolute value of whatever your a is. Remember, if your a is negative, that's just going to reflect the graph in the x-axis. The range, if it's amped up or down, the range is going to change, right? It's not just going to bounce between positive 1 and negative 1. If it's amped up, it's going to bounce between larger values further away from 0. Or if it's amped down, it's going to bounce between values closer to 0. So the range will change if the amplitude changes. It'll be negative the absolute value of a to positive the absolute value of a. And notice it's brackets, not parentheses. That's because our graphs are solid lines like this. If it were solid with, let's say, a hole, or it became dashed, those represent not included, so we would use parentheses, but ours are solid, so it includes that height of positive 1, height of negative 1, or whatever the amplitude changes it to. That is why we're using brackets here. Okay. Below is the graph of y equals 2 sine of x. We're being asked to find the amplitude and the range. Okay, so take a look at that graph. The first thing I want you to do is identify the parent function. What color is the parent function? Well, the parent function is represented for us here in red, okay? It's a dashed line, not because sine is dashed or open, but because it's not our actual graph. They're just using it as a visual aid. This here in this red dashed line, it's not actually on our graph. It's just a visual aid for us. Sometimes we call that a hidden line. And this visual aid is saying, all right, this is the parent function, y equals sine of x. The blue one is what we're interested in. We are being asked what is the amplitude and range for y equals 2 sine of x, this blue one here. Pause the video, see what you come up with for amplitude and range. All right, welcome back. If you came up with the amplitude is 2 and the range is from -2 to +2, you got it right. Now let me elaborate. Remember, definition up here. Amplitude is absolute value of A. A is the coefficient in front of sine. So here, our A is equivalent to 2. We know that A affects the amplitude. So this one is being amped up to 2. You can see that based on the equation right here. You can also see it based on the graph. The parent function has that amp of 1, but the blue one is being amped up to -2, +2, -2. That's also how you can see the range, or using the formula, we have A is equal to 2, therefore the range is negative absolute value of 2, comma, absolute value of 2, or -2 to +2. Let's talk about the period in more detail. The period of a periodic function is the distance along the x-axis that it takes for the function to complete one cycle. The graph of y equals sine bx or y equals cosine bx with b greater than 0 has a period of 2 pi over b. Okay, for our parent function, b was equivalent to 1. Okay, that's for the parent function. So the parent function has a period of 2 pi divided by 1, which is simply, or simplified, to 2 pi. And we know that it's 2 pi radians, one time around the unit circle, or one period of that periodic function. So it's 2 pi over b. Now, if b changes, like in this example here, below is the graph of y equals sine of 2x. This is b, it's the coefficient in front of x. If b changes, then it's going to affect the period. Please be careful not to accidentally say that the b is the period, okay? That would be saying that the period is 2. Well, you can see here, one period of sine, it's taking pi many radians to complete. You see here, sine, so starting at the origin, because we know sine starts at the, well, one cycle of sine starts at the origin, crosses through it, goes up, down, right there it stops. So this right here is one period of sine, and it's being completed in pi many radians. So b being equal to 2, 2 is not the period. 2 has just affected the period. Let's figure out how it has affected it. Okay, parent function visual aid is right here. Parent function has a period of 2 pi. So we take 2 pi, and we're going to divide that by b. And in this function, y equals sine of 2x, b is equal to 2. So we're going to take our 2 pi and divide it by 2, which simplifies to our new period of pi. So you can see that with the, you can do the work from the equation there to get the period being pi, or you can see it visually. One cycle of sine is occurring each pi many radians along the x-axis. Here it goes again. Here's another cycle of sine. Done. It took a distance of pi. Here's another one. Let's see. Has to start low. So here's one period of sine. Goes up, down, and back. That one period of sine took a distance of pi many radians along the x-axis. So the answer is, if b equals 2, the period is pi. Note, the three values to plot between 0 and pi are 1/4 of the way to pi, 1/2 of the way to pi, and 3/4 of the way to pi. I want to erase all this annotation so that I can talk about that a little bit. So this is going to be important in sketching the transformed parent functions. Okay, it says the three x values to plot between 0 and pi. Okay, so for this example, 0's right here and pi's right here. And we just talked about that is the distance covered to complete one period of sine. Okay, so we're focusing on just this one right here. Okay, so we know the start of it and we know the end. But there are 3 points between the start and the end of cosine that are of interest to us, that help us graph. They are, start at your starting point, and you go 1/4 of the way to the end of sine. It's like going 1/4 of the way around the unit circle, if that helps you. So we're right here. And then we go halfway to the other end of the period. It's like going halfway around the unit circle of the parent function. And the next one is 3/4 of the way. So you can see they're equally spaced. These 3 points between help guide our graph of sine. At the first point, we should reach our maximum. At the second point, we should be back to where we started, the origin, non-translated at this point. Next, to get 3/4 of the way through, we're at our minimum, and then to the 5th point brings us back to the x-axis. So that's what this note means down here. To summarize, you have a starting point when you're sketching sine, an end point, and these 3 points here are evenly spaced between. Goes to the max, back to 0, min, and back to 0. All right, let's look at the graph of y equals cosine 2 over 3x over 1 period. Okay, so we're being asked to graph this one this time. So we're going to go in alphabetical order, starting with lowercase a. Well, lowercase a is the coefficient in front of cosine. We don't see 1, that's because it's invisible or implied, it's 1. So a equals 1, keeping our amplitude at 1. B, on the other hand, okay, so this one was A, and this one is B. B is not the period, but B is going to affect the period. So how is B going to affect the period? Well, B is 2/3. So we take the current so we take the current 2 pi and we divide that by B to get the new period. So 2 pi divided by 2/3 is 3 pi. So this is our new period. So it's going to take a distance of 3 pi radians to complete 1 period of cosine. All right, so we're going to graph this now. We're going to start with 0 and 3 pi. It's going to be our 2 points, 0 and 3 pi. And then we're going to plot the 3 values between 0 and 3 pi. And we know those are going to be 1/4 of the way, half the way, and 3/4 of the way. From 0 to 3 pi, 1/4 of the way there is 3 pi over 4. From 0 to 3 pi, half the way is 3 pi over 2. And from 0 to 3 pi, 3/4 of the way is 3 times 3 pi over 4, or 9 pi over 4. When we graph that, we want to set it up so that we can show a full period going from 0 to 3 pi, which we have. So for cosine, we're starting here up high. We're ending here up high. And our 3 points in between that help us sketch cosine are 1/4 of the way there, we're at x equals 0. Half of the way there, we're at the minimum. and 3/4 of the way there, we're back to x equals 0. And when we get to the end of our period, it's just one period in this example, by the way, pointing that out. If it had said graph cosine of 2 over 3 pi, that graph continues in both directions, but it's nice for learning purposes just to look at one period so we can see the start, the finish of one cycle, and the 3 points in between. All right. When a is negative, we have discussed how the graph is reflected in the x-axis. So let's use this example. Graph y equals -2 sine of 3x over 1 period again. Okay, so alphabetical order, we're going to start with a, which is right here. So that's going to affect our amplitude, and then we're going to talk about b, which is 3. That's going to affect our period. All right, let's write it up. A is equivalent to -2. That makes our amplitude +2. Amplitude is a distance traveled away from the x-axis, so it has to be positive. And a is negative, so the graph is going to reflect across the x-axis. Okay, so that's already a lot going on to our parent function. Let's look at b. b is equal to 3. So we're going to take our parent function's period, which is 2 pi. We're going to divide that by 3, and now we have our new period. So it's going to take a distance of 0 to 2 pi over 3 to complete one cycle of this sine. This sine is also going to be amped up, so it's going to go up to 2 and down to -2. It's also going to be reflected in the x-axis. So 3 transformations are occurring. Reflection, it's being amped up, and the period is going from 2 pi, it's being shrunk down to 2 pi over 3. Okay, let's start with our graphs of the 2 points on our graph of 0 and 2 pi over 3, okay? It's the starting point and the ending point. And this is sine, so remember with sine, our starting point is going to be on the x-axis. Our ending point is also going to be on the x-axis. And then the 3 points in between are, this is 2 pi over 3. So if you go 1/4 of the way to 2 pi over 3, just think about it as multiplying by 2 pi over 3 times 1/4, okay? 2 pi over 3 times 1/4 is 2 pi over 12, which simplifies to pi over 6. So 1/4 of the way, we're going to be at pi over 6. Half of the way, think about taking your 2 pi over 3 and multiplying it by 1/2. You'll get pi over 3. So half the way there, we're going to be at pi over 3. And 3/4 of the way, again, just think of your 2 pi over 3, think about multiplying that by 3/4. And that will become 6 pi over 12, which reduces to half of a pi. Okay, so 3/4 of the way there, we're at half pi. So if the period was the only thing that was affected, our sine function would bounce between +1 and -1. It starts here at the second or quarter way through, it's at its max. Halfway through, it's back to the x-axis. 3/4 of the way through, it's at its minimum. And the final quarter of the way through, it's back at the x-axis. So this would be our function if the only thing that was affected was b changing from 1 to 3. So this graph right here, its name is y equals sine of 3x. But we've got 2 more things to do to this. We need to amp it up to 2. That's pretty easy. It's just 2, write your -2, and so when you do your max and your min, go up to +2, down to -2, and you've amped up, okay? The last thing is the reflection. Remember that the reflection is in the x-axis. So every point above the x-axis will have a mirror image or reflection on the other side of the x-axis. So let me change colors. and I'm going to show this amped up function if its mirror image or if its reflection in the x-axis is graphed. This point, well, that point's on the mirror, so it stays there, but then the reflection goes like this. Right here, when it hits +2, the reflection is hitting -2. Here it meets right back up. We're at the mirror again. Then when the non-reflected goes down to -2, the reflected is up at +2 and then meets back again at the mirror. So that's my little sketch. Hopefully you can see the development of it leading to this final graph right here, whose name is y equals -2 sine of 3x. One more slide and then we'll stop and do some homework. All right, we're being asked to graph y equals -3 cosine pi x over 1 period. All right, alphabetical order. A for amplitude. A is -3, so our amplitude is +3. That also means, since A is negative, that we're going to be reflecting in the x-axis. So 2 transformations already, amping up and reflecting. All right, alphabetical order. After lowercase a, lowercase b. B is pi, and that is not the new period. That is going to affect the period. So if b equals pi, we take the parent function's period, which is 2 pi, we divide it by b. And in this case, that's 2 pi divided by pi, which is just 2. Okay, so it takes 2 distance along the x-axis to complete 1 cycle of cosine. Okay, so let's start our graph. We're going to start it at 0 and end it at 2, and we want to find 3 points of interest between. From 0 to 2, if we go a quarter of the way there, we're at 1/2. From 0 to 2, halfway there, we're at 1. And from 0 to 2, 3/4 of the way there, we're at 1.5, or 3/2. Okay, I want to show the development of this. I'll just sketch it here. Okay, so we're going from 0 and hold on, this is cosine. So I'm going to leave that point there, but that is not a point on our graph, okay? We know cosine starts up high. I'm sorry, we know cosine does not cross through the origin, I should say. So I'm going to leave that point there, but it is not a point on our graph. I'll make our graph a different color. Okay, now we're going to end at 2. Where is 2? Well, just to give it some reference, pi is 3.14. So 2, if let's say this were pi radians, 2 would be about here. So we're going from 0 to 2. And we're going to highlight the 3 points between, a quarter of the way through, half of the way there, and 3/4 of the way there. Okay. Now, let's talk about cosine's actual points. I'm going to change this back to blue. Okay. So if that were the only transformation occurring, if b was equal to pi and that's it, it's the only transformation, then we're going to start up at 1. Here's 1 point on cosine. We'll pass through at a quarter of the way. We'll get to the minimum at -1. We'll pass through 3/4 of the way, and then we'll get to our maximum back at 1 when we get all the way through that period of 2. All right, so this graph right here is 1 period of the sine of the function y equals cosine of pi many x's. But we have 2 more transformations to apply. That is amping up, so it's going to not just bounce between +1 and -1. This is actually going to bounce between positive 3 and negative 3. So let's amp this up. I'm gonna go like this. Whoa. That is a really bad sketch, but hopefully you get the idea. I'll show you a visual that looks a lot better. And then finally, last transformation is the reflection in the x-axis. So we're actually going to start down low, pass through, then max out, pass through, end up there. Okay, let me show you the graphic. Here it is. This is the graph of y equals negative 3 cosine of pi x. Okay, let's pause and do homework questions. This is chapter 4. I want you guys to do numbers 1 through 18. My name is Jami Emigh. Thank you for being here, and I will see you soon for our next discussion.